Hi.
Hi, are you sure this course is just for 2499?
Yes, and you know this is the only course with this expertise across the world.
No way!
Yes way. Don't delay. Enroll now.
Geeks learning together.
Hi.
Hi, are you sure you can prepare for product based companies through this course?
Yes, sitting at home?
No way!
Yes way. Don't delay. Enroll now.
Geeks learning together.
Hello, guys, and welcome back to this amazing channel, Geeks for Geeks Practice. This is Abhinav, and today we are back with our next problem of the day. Uh, okay, yeah, I think there was a network issue. Yeah, yeah, guys. So hello and welcome back to this amazing channel, Geeks for Geeks Practice. This is Abhinav. Today's our problem is good subtrees. First of all, please confirm if I am clearly audible and visible to you all. This is perfect time for me. Yeah, we know Nakaj. I have conveyed this matter to the team. Team will decide whether we have to keep it in this time or like 12 or not. Okay, great. Uh, okay, great. Audible, visible, great. So, correct, guys. Today's problem is quite easy. It's not that much tough. Okay, it's let's see what the problem is. Okay. So, guys, the problem says that we have to count good subtrees. And what are good subtrees? Good subtrees are those which have number of distinct values less than equal to k. So we have a k, and for the particular tree we have to find that in a subtree how many subtrees are there which contain uh, distinct values less than equal to k. Okay. So let's say if this is a subtree they are giving us, this is a subtree that they are asking. So there are multiple subtrees inside a tree. Okay, so if this is a tree that we are having here, okay, so if you will see, this is the subtree that we are considering. Okay, so wait. So you can see, guys, here one thing. Okay, that this is the first tree. Okay, so in this case, they are saying that your case two, your case two. So how many subtrees are there which contain number of distinct element less than equal to 3? Perfect time for me also. Okay, Aman. Okay, so if you will see here in this whole tree, number of distinct elements are nothing but 1, 2, 3, 4, and 5. 5 distinct elements are there, which is not less than equal to k. So it is not considered. Now you will see this particular subtree has two distinct elements, means it is possible. So 1. You can see this particular subtree has also one distinct element. It is also possible. This has 3, not possible. This has 1 and this has 1. So means there are 4 subtrees. You can see answer is 4. There are 4 subtrees which have distinct element less than equal to k. Am I right? Okay. I hope this logic is clear. So guys, what I will do is I will take here. No guys, because we want distinct values. Okay. So which data structure is used to store distinct values? If you remember, set is used to store distinct values, and more preferably we can use unordered set, because here we don't want sorting, we just want distinct elements. So if we can take an unordered set will only store the dictionary element or the unique element. Simple. Okay. So what I will do, I will take here not unsorted, unordered. Okay. So I will take here a function, let's say count, and that function will return us a set. Okay. This count function will return a set. Okay, which will contain all the nodes in that particular subtree. Okay, and I will take here an answer. Okay, guys, great. So first of all, I will say if. So first of all, I will take here a simple unordered set. I will take a simple unordered set. So if my root is null, so guys, if the root is null, so that simply means that in your tree nothing is present. In your tree nothing is present. So simply return your empty set. Okay. Now guys, now let's say that you are at your root. So when you are at your root, so first of all, what you will insert in your set? So first of all, you will insert the value at your root. So in my set, I will insert what? My root data. So my root value is inserted in a set. Now what I will insert? So guys, now I will insert the values of my left subtree and values of my right subtree. And how we can find the values of my left and right subtree? So for finding the values of left and right subtree, I will have two different recursion calls. So first recursion call will be, let's say, of left, in which the same function will be called, but for the left subtree. And similarly, one more recursion call will be done where it will be called for the right subtree. Okay. Now, guys, what I will do now, like, see, this S contains my root. This left set contains nodes of the left subtree. Right contains nodes of the right subtree. Now I will insert the nodes of left and right both inside your main set. So now I will iterate from this left and from this right. So for iterating, we know we can simply use this iterator, auto, and it. Okay, and I will insert this thing in my border. So first my left set and then my right set will be inserted in border. Now this set contains number of distinct elements in that particular tree. In that particular tree. Exactly, you're right, Rishit and Nekas. Okay. Now, guys, if the size of this set is less than equal to k, because we want our size less than equal to k. So in that case, I will increase my answer. I will increase my answer because I have to count number of subtrees having dictionary element less than equal to k. And at the last, I will return my. Okay. Now simply, guys, I will have this count function with my root and k, and at the last I will return answer. Simple. That is what we are having here. Okay, let's run it. Let's submit this. You can see all the test cases have been passed. Okay, all the test cases have been passed. If you talk about the time and space complexity, so it is written here. Actually, that space complex is same. Here they are assuming the recursive is stack, but if you not assume, you will simply it's n into k. Okay, why? Because like simply we are checking for each and every subtree. Okay, so usually there are n subtrees in a in a tree. Like every node has a subtree, na? From every node we have a subtree. This is a subtree, so we have n subtrees. So usually that's the time complexity. Okay, so that is what we are having here, guys. Okay, this is what we are having here, guys. So I hope this approach is clear to everyone. Please write a +1 if this is clear to all of you watching this. If you want, I will share the code also. Yeah, it's something similar to that, exactly. Yeah, in our case, it's order of n. They are saying order of n into k, but in our case, it's simply order of n, exactly. It's order of n, exactly. Because we are just checking for each and every subtree. Yeah. Uh, hmm. Okay. Maybe like because in every recursion call we're also having this thing, by the way. But because you can see key the value of n is very like 10 to the power 5, so it will be order of n. Okay, great. Okay, so great guys, I hope that you have got this particular video. Let's meet again tomorrow with the next problem of the day. So guys, tomorrow time will be same, it will be 6 p.m. For today I was quite busy at that time, so we have rescheduled it. I know that the time at 6 is quite not feasible, but I've talked with the team regarding that. So let's continue with this time for now. Let's meet again tomorrow with the next VOD. Thanks for the video. I hope you are fine. Thank you. Good night. Take care. Happy coding. GFG कर लो हो जाएगा.